So hopefully you've had a chance to catch up, look over some of the old videos and get back up to speed if you're watching this series. And hopefully by now you have this KeyManager data type filled out. Again, I gave you the data type fields in the last video, so if you haven't figured it out, go ahead and just freeze the screen and go ahead and fill it out yourself. Okay, so I'm going to go ahead and move on now. We'll need to look at this stuff on and off. Anyway, so the KeyManager class, the init function is responsible here for basically determining if it's a Dallas key, or I'm sorry, if it's a Dallas 1995 key or 1996 is the actual key they use, but it doesn't matter. And then the clears out the data, makes everything in the class 0, and then reads the data and then copies it to the various fields. That reads the raw data from the key. However, in this read, or something that read calls, that's where things get tricky, because not only does it access the USB device to read the data, read the key data, pull it in, it does some decrypting of data, and it looks like in this version it does more stuff to protect the data, I think, than the Force version. Okay, the Force was pretty straightforward, but this one seems to do a little bit something different. But let's go ahead and read through what we have here. So we have the read class, okay, grabs an instance of the USB IO device. Just like before, we basically set a bunch of things to zeros. I call them memsets because that's the C function that's used, or B0 in C. They probably called here that this is what got turned into the code. And then it memsets the actual raw key data to 0. And then if the key is a 1995 Dallas key, I'm sorry, if it's not a 1995 Dallas key, it does this code down here. But we know we're going to have a 1995 Dallas key. So actually, let's go to this code from here to here, so we can skip all the way down to here. So we're in this else loop, and I've commented a DS1995 key reading code. And what it does here is it does this 3 times, read DS995 key data with B40 failover. Okay, what is that? We'll have to find that out. And it looks like what it's doing here is just actually literally doing it 3 times in case it fails, and then if it doesn't work after the 3rd time, it's going to probably go quit. So really we only have to concern ourselves with the one instance of this. Alright, so it's going to do some magic interacting with the IO device and bring back that data, and we'll want to look at that. But assuming it brings back all that data, what happens now? Well, it looks like it copies, it opens a file, and this is the Megatouch developers code that they put in here so they can obscure file names. If you watch the Hacking the Force videos, you've seen this before. What here is they have actually just an encoded string. It's probably just an XOR, and it's probably just XOR with this data here, I'm imagining. And this data is just a global variable, which is probably not filled out, so it gets probably filled out at some point. But basically it's opening a file name. They don't want you to see what the file is. Fine. There's easier ways to, well, we can either reverse engineer that if we care, which I don't care about, because when we give it when we fix whatever this raw key data is, it doesn't matter what the file name is, because it's going to open the file name and then it's going to write the K laser into that file name. The K laser is actually the full key that is etched on the back of the Dallas key, and that is not actually in volatile RAM on the key. It's actually hard-coded into the key. So it's basically writing the key serial number to a file, and it writes it somewhere else, which is all kinds of fun and interesting. I don't know why it's doing that, but I also don't care why it's doing that. I'm kind of curious just to decrypt this thing here to see what the file paths are, but I don't actually really care, because by the time we fix all this, the data is going to be there, and I don't really care. So, alright, we skip down here, and then it says if the Dallas key is 0, well, we're not going to have a Dallas key is 0. Our field is going to be Dallas key 1, so we skip this from here to there, and then we get to exit. It's going to parse the option data, which it read from the key, and then it's going to copy some information out of a buffer to country description, and then it's going to set a variable in the KeyManager class to 0, and then a global variable to 0. And nothing, we don't really care about anything here. Doesn't affect us. Basically, we need to understand what's going on in this read DS1995 key with v40 failover code, so we can figure out how to replace the actual key data from the key with something from the hard drive. All right, so let's look at this read DS1995 key data with v40 failover. Very simple function. It tries read DS995 key data with the USB IO class destination, what looks like a length, and I'm pretty sure it is. Yes, it is. It's a length. So length, and then this thing, which is 0. We don't know what that is yet. Return code equals 1. If the value is 0, it tries it again with an option of 1, and then it returns. I don't quite know what this 0 or 1 is yet, but we're going to look at it. Okay, so we have 0 or 1 or 1. All right, so that's pretty simple. Basically, it's just a pass through to read DS995 key data. It's going to do it potentially twice, but it's going to change the argument the last argument the second time. So we have to understand what that's doing. So here we go, and this is going to be basically the meat of the problem, I think. Let's see what's happening here. We have the USB IO device, a destination buffer, a size to read, and then I just called it footer based on what I see later in the code. Don't know what this is yet. Okay. But everything else is pretty straightforward. The destination is going to be where it's going to write to that raw key data in the KeyManager class. The size, we know it's going to be, because we looked at it when we called it, it was 3F0, I believe, which is 1008 in decimal. So what are we going to do here? All right, well, we're going to memset two buffers. We have two buffers, each of 1024 bytes. And we're going to set them all to 0. That's, again, standard practice. You always initialize your variables in a function so they don't have just random data in there. If destination is 0, that's an error condition, and it's going to basically give you an error. So destination should never be 0 because you can't write to 0. It's not a valid address. Actually, you can on older versions of Unix, and there was security. Never mind. If size is less than 2, so it's that's an error condition. We don't care. We're not going to have an error condition there. So then we're going to check the USB. Found USB. If found is 0, we're going to return 0 because we can't obviously access a USB device without the USB hardware. That is that I/O board. It's going to do a lock, and then here comes a read footer thing. If read footer equals 0, read footer, it's going to call this function. Okay, and see how it results. If it returns a value, it's going to set a field to that result. Otherwise, it's going to set that field to 5. And I don't know what this is doing yet. We'll find that out as we go on. I think this is some magic to try to make it harder to hack. And it may be that what this is doing is actually trying to find where the data is, because one of the things they did in the old key, in the Megatouch Force 2011 key, there was, I don't remember how much data the key stores. I think it's like 64K or something. I don't know, or K bits. I don't even know. But basically, it only used about 1024 bytes, and it was all at the beginning of the file, or the beginning of the key, and everything else was set to 0. In the 2014 version, rather than just having the data at the beginning, at least in the one key I looked at, and a bunch of zeros at the rest, there is scrambled data everywhere, and somewhere in that scrambled data, in one of the blocks of data, the actual key data is. They didn't do a really good job of hiding it because all the data that's scrambled is actually the same pattern, and the block of code that actually has the real key data is different. So it's really easy to find where the actual data is hidden. So maybe this is actually telling us going to tell us what block it's in. I don't know. And it would be interesting. Maybe on each key they moved that block. Who knows? I don't know. I don't know yet. That's what we're going to figure out. So we're going to come back to this. We just know that there's going to be this function read footer that we have to understand. It's probably going to have some obscure or obfuscated type of code, I'm guessing, to try to hide what's going on. This is definitely new. I do not recall this at all from the 2011 Force version. Okay, and so then we're going to do this command request, which is actually a libUSB request to actually interact with the USB protocol. Oops, sending some data there. So we might have to look at this, but we're going to skip over that for now. If this USB command thing returns a 0, that's an error condition, an X, and then it looks like it's going to read USB memory. It looks like, I think that's 1 byte of data it's going to read at this offset, and store the results to is security detected. So here looks like it's actually checking to see if the real security key is there, and if we take that out, we're going to have to patch this code, so it just doesn't do that anymore. It just returns 1. So then, assuming we patch that out, if 0 in this case I actually believe is success. It's not equal to 0, that means failure, and it would go to the end here, which security key is not detected, and it says basically there's again an error and an exiting. So if it's not a failure of the read accessing the USB memory, then it checks to see the value security key detected is not 0. So assuming that the security key is detected, we're going to enter into this area, which it looks like it's just going to read the USB memory, and it looks like it's going to do this in blocks of 128 bytes a bunch of times, and fill in. Yep, it's filling in the data. It's actually writing it to the USB instance pointer is actually, in this case, it's actually no longer a USB instance pointer. It's actually a pointer to this buffer. It's interesting, the code. It's probably this variable is being reused, and somehow I screwed up the labeling here. But this actually, in this line, it's actually setting it at the beginning of the buffer, and then it's reading the buffer, which is getting incremented by 80 or 128 bytes every time. So it's just going to read this in a loop. And this is interesting. I'm going to make note of that earlier because this looks like where the data is actually stored at, where it's looking for the data, or where the offset in the USB I/O board accessing is. So anyway, yep. So this is, we're going to go ahead and mark this in, or we're going to do read in encrypted data, 128 bytes at a time. And then it's going to copy the data from the one buffer to another buffer of the same size. Then what it's going to do is, this is where it actually generates the decryption key. It grabs the USB key ID, which is that 8-byte serial number, and it only cares about middle 6 bytes, because that actually, the first byte and the last byte are not actually part of the key ID. This is the unique serial number, they're a family name, and I think it checks them. So it's discarding those, XORing it with some magical numbers that are just hard-coded in here. In all the versions I looked at, these numbers always change. So it's taking the actual serial number 1 byte at a time, XORing it with, in this case, 60, and then the next byte 62, and then 6E, and these are hex again, not 62, it's hex 62, 72, and 6F, and then 75. Okay, so based on that, it's going to actually go ahead and generate an encryption key. Then it's going to write that encryption, this area here, it's going to write an encryption key 6 bytes of the generated encryption key back into the buffer data. Okay, it's going to store that. And then it's actually going to decrypt the data, but it's going to skip the bytes that it actually manually wrote into there. Okay, so it's actually writing into bytes 18 through 23 in the data buffer, the decryption key, and then when it's going through and decrypting each byte of data against the key, or against each byte of the key, it does it 6 bytes at a time, 1 byte at a time. So the first byte is decrypted with byte 1 of the key. It's XORed, basically. That's their decryption. The second byte is XORed with the second byte of the key, up to the 6th byte, and then it starts again at 0. So it's going to decrypt the data, skipping these bytes, because that's what we just wrote into it. Then it looks like here, oh, that's still there. Then it's going to compute the key checksum. Okay, and then it's going to make sure that the checksum it computed, it's going to actually compute the checksum, and then it's of all the data that it just decrypted. And then it's going to actually go ahead and it's going to go ahead and check that against the this is the raw data. It's going to actually check that against the bytes in the raw data where the checksum is stored on the key and make sure it is okay. If not, it's going to error out, and that's it. So basically, again, we just have to defeat this call here where this read USB memory, rather than reading from the key, it's reading from the hard drive. However, and we have to make sure the security key actually is detected when it accesses this call. And we also have to, in the next episode, have to figure out what this read footer and command request, or the read footer does. And I want to know what this command request does. So we'll have to get into that. But we're getting really close. It may be worth it just to actually change out these and see what happens, and not even worry about the command request and footer, and just see if it actually works. Maybe these things actually have nothing to do with any security additions or whatever, and maybe I'm wrong about that. I think it's gonna. I think this is another level of security check, but I don't know. But that would be a reasonable thing to actually just patch these things out and try, and maybe it might just work as is. What I might do, rather than patching the code, the binary, what I really want to do is make a shared library and hook the underlying USB calls specifically to the things that we care about. Or this, I don't even know. I think this is stored read USB memory. Yeah. It basically goes to the libUSB library and make some calls. So it may be fun. Actually, I think it would be much better, much more interesting and clean to, rather than patch the binary, to just make a shared library that gets loaded first, overrides the libUSB control transfer, and when the specific calls out to the key happen, just override, just plop the data in. I don't know. We'll see. We'll see about that. I haven't decided which method I want to go. Maybe I'll hack the binary first so I know what actually has to happen, and then change it out with use the real version and just change out a shared library. That would be a so much cooler, cleaner path to do than hacking the binary. And that would actually work into my next project that I'm thinking of, which is to virtualize the entire USB I/O hardware, or the USB card, because I don't think it does anything but actually, besides allowing access to the key, I think it stores some non-volatile data for like settings and things, and bookkeeping. I think there may be a sound device on there, or it might be some type of pass-through. I'm not sure about that, but either way, I'm sure we could redirect the calls to other sound hardware, because they are USB calls. So who knows? We'll find out. And I could be wrong about the sound altogether. I thought I remembered my sound plugging into that board directly, but who knows? Okay, that's it for today. It's been a long episode, so